Good morning, everybody. Part two of our notes. So if we look at page two, what we want to accomplish today is taking a look at how to test for independence, which we've done a little bit already. We've introduced that formula. We've got two ways to really test for independence. This is the one that we've seen already, where we take the probability of A, multiply it times the probability of B. If that equals our probability of A and B, the events are independent. Since we've now discussed our given and our conditional probability, we have another test for independence. I typically use this one. I will show both of these in the notes today, so you can make the choice of which one that you want to use. So if we look at the first example, it's just basically plug in the numbers and check. Probability of A times probability of B, does it equal the probability of A and B? So we got a situation where A is 0.4, B is 0.3, and our A and B is 0.12. If we multiply these two guys together, we do see that 0.12 does equal 0.12. These two events are independent. So if we look at example 2, same formula. I got A at 0.25. B is 0.6, and we're testing to see if that is equal to 0.85. If we multiply these two guys together, we find that we get 0.15, which does not equal, and those guys are dependent. Third example that they give us a Venn diagram. So let me sketch that guy up here real quick. I got A, B, and the overlapping. So my probability of A. Remember, A is whatever's inside that circle there. So I got 0.3 times my probability of B. That is everything that is inside that circle, which is 0.5. The and, we recall from that, where we find our and, we find the and in the overlapping portion of it. 0.2. Multiply these guys together, I get 0.15, which does not equal 0.2. Those guys are dependent. So that's just if we want to test for independence, given all the information. So let's flip to the next page. Look at the two-way frequency table. You guys have done two-way frequency tables in the past. I have already gone ahead and filled out our two-way frequency table here with the information. So what we're going to do is go through and look at all the probabilities of these. One of the things I want you guys to focus on, if we see the word given, we are going to focus on kind of these subtotals here, the 18, 18, 16, and 20. All right, that's if we see the word given. All right, if we don't see the word given, we're going to be taken out of our total of 36. All right, so if the first one we're looking at, probability of the student chosen being a senior. All right, so we're looking at all the seniors. Okay, well, that is our 20. So probability of a senior, that is equal to 20 out of our 36. Next one, probability the student chosen owns a car. So I've kind of color-coded these. So to stay with that, probability of owning a car. That is our orange. 18 people own cars out of 36. Third one, probability student chosen is a junior and owns a car. So if we're looking at a junior and owning a car, we're looking for where those two sections meet. Junior own car, that's 6. So probability of junior owning a car, that is our 6 out of 36. Probability that they are a senior and they own a car. So staying with our color coding, probability senior and own a car. Own a car seniors, that's our 12 out of 36. If you notice, all of these are out of 36, or out of our total. Okay, we look at number 5, and they start talking about a conditional probability. We start introducing the word given again. So what is the probability a student chosen is a junior given that they own a car? So going back to what we did yesterday, once we see the word given, I'm only giving you the people, in this case, that own a car. So I'm only looking at these 18 people right here. Of those 18 people, so the probability that they are a junior, remember that line means given that they own a car. So, probability that they are a junior given that they own a car. So I'm looking at the 18 people that own a car. Of those 18, how many are juniors? Well, we've got 6. So we'll keep this color-coded. 6 out of our 18. Okay? Remember, I'm only looking at the people that own a car. Next one, number 6. Probability of student chosen owns a car given that they are a senior. So, probability that they own a car given that they are a senior. Okay? So I'm only looking at the seniors. I'm only looking at those in red here, our 20 people. So out of those 20, how many of them own a car? How many own a car? So 12 of them. 12 of those seniors own a car. So are these guys independent? This is our last part here. So we can do a couple things. Probability of A and B equal to probability of A times probability of B. Alright, so R being a senior and owning a car independent. We're going to make senior be A. Own a car is going to be B. Alright, so probability of them being a senior. Alright, that is 20 out of 36. Owning a car, 18 out of 36. Probability of being a senior and owning a car, where those two things overlap, so 12 out of 36. If I simplify these, this is 1/3. Is that equal to 5 over 9 times 1 over 2 when I simplify these? Well, as we see, 1/3 does not equal 5 over 18. Therefore, these guys are dependent. So that's the way using this formula. To look at it the other way, probability of A given B, seeing if that is equal to the probability of A. Alright, so probability of A given B, does that equal the probability of A? Alright, remember that A was being a senior. Alright, so probability of them being a senior given that they own a car. Alright, so that is our 12 out of 18. Is that the same as the probability of them being a senior? Well, we have 20 seniors out of 36. If I simplify this, 2 out of 3 does not equal 5 out of 9. So either way we do this, it shows that they are dependent. Once again, if you guys have any questions on this, let me know. Keep up the good work. Keep working on doing those quizzes, getting them up to 100. And I will talk to you again soon. Have a good day, guys. Bye.